Go floating point types. Question: what floating point types are available in Go, and what is the default type? Go has two floating point types, float32 and float64. Float32 uses 4 bytes and has about 6 to 7 decimal digits of precision. Float64 uses 8 bytes and has about 15 to 16 decimal digits of precision. There is no type called float in Go, so you must choose float32 or float64. When you write a decimal number, like 3.14 using short variable declaration, the default type is float64. Question: how are float32 and float64 stored in memory in Go? Answer: in Go, floating point numbers follow the IEEE 754 standard. A float32 is stored using 32 bits. It has 1 bit for the sign, 8 bits for the exponent, and 23 bits for the mantissa. A float64 is stored using 64 bits. It has 1 bit for the sign, 11 bits for the exponent, and 52 bits for the mantissa. You can use functions from the math package like float64bits and float64from-bits to see the binary form of a float64 value and convert it back to a number. Question: what are different ways to write floating point literals in Go? Answer: in Go, you can write floating point numbers in several ways. You can write a normal decimal number like 3.14. You can write 0.5, which means 0.5, or 1 dot, which means 1.0. You can use scientific notation like 3.14E2 for 314.0 or 3.14E-2 for 0.0314. Go also supports hexadecimal floating point literals such as 0x1.fp4. You can use underscores to make large numbers more readable, for example 1,000,000.5.
Question: how do hex floating point literals work in Go? In Go, you can write floating point numbers in hexadecimal form using the format 0x mantissa p exponent. The exponent is required and it represents a power of 2, not a power of 10. For example, 0x1 p10 means 1 times 2 to the power of 10, which is 10,024.0. Another example is 0x1.8 p1, which means 1.5 times 2 to the power of 1, and the result is 3.0. What special floating point values exist in Go, and what should you know about them? Answer: Go floating point numbers can represent special values such as positive infinity, negative infinity, NaN, and -0. You can create them using functions from the math package. NaN means not a number, and an important rule is that NaN is not equal to itself, so nan equals nan is false. You should use a function like isNan to check it. Infinity values follow special arithmetic rules. For example, positive infinity plus positive infinity is still infinity, but positive infinity minus positive infinity becomes NaN. Go also supports -0. -0 looks equal to 0 when you compare them, but it has a different sign bit, which you can detect using sign bit.
Question: why is using NaN as a map key dangerous in Go? In Go, NaN is not equal to any value, including itself. Because of this rule, every time you use NaN as a key in a map, it is treated as a different and unique key. If you insert several values using math.NaN as the key, the map will store all of them separately. The length of the map will grow and you will not be able to retrieve those values in a normal way. This can cause serious bugs, so using NaN as a map key is very dangerous. Question: why should you not compare floating point numbers with double equals in Go? Answer: you should not compare floating point numbers with double equals
because they are not always stored exactly in memory. Many decimal numbers, like 0.1 and 0.2, cannot be represented perfectly in binary form. When you add 0.1 and 0.2, the result is slightly different from 0.3. Because of this small difference, the comparison 0.1 plus 0.2 equals 0.3 returns false. This happens due to floating point precision limits. Question: how can you safely compare two floating point numbers in Go? Answer: instead of using double equals, you can compare the difference between two numbers and check if it is very small. This small value is called epsilon. You subtract one number from the other, take the absolute value, and see if it is less than or equal to epsilon. If the difference is small enough, you treat the numbers as equal. This method avoids problems caused by floating point precision errors.
Question: why is relative epsilon better when comparing large floating point numbers in Go? Relative epsilon is better for large numbers because it compares the difference based on the size of the numbers. First, if the two numbers are exactly equal, it returns true. If not, it finds the absolute difference between them. Then it checks how large that difference is compared to the larger of the two numbers. This means the allowed error grows with the size of the numbers. For very large values, a small fixed epsilon may be too strict, so relative comparison gives more reliable results. Question: what happens when you convert floating point numbers in Go? Answer: when you convert a float 64 to float 32, you can lose precision because float 32 has fewer bits. This means the value may change slightly after conversion. When you convert a float to an int, Go truncates towards 0. For example, converting -3.9 to int gives -3, not -4. If you want proper rounding, you should use a function like round before converting. Also, if you convert a very large float to an integer type and the value is outside the valid range, the result is implementation dependent and may not be what you expect. Question: what are the main rounding functions in Go, and how do they work? Go has several rounding functions in the math package. Math.Floor rounds a number down to the nearest integer. Math.Ceil rounds a number up to the nearest integer. Math.Trunc removes the decimal part and keeps only the integer. Math.Round rounds to the nearest integer away from 0 for 0.5 values. Math.RoundToEven rounds to the nearest even number when the value is exactly 0.5, also called banker's rounding. Question: how can you format floating point numbers in Go using fmt.Printf? Answer: in Go, you can format floating point numbers with fmt.Printf using different verbs. The f verb prints the full decimal value. You can limit decimal places with something like %.2f. You can also set a minimum width, for example, %12.2f, or pad with zeros using %012.2f. If you want scientific notation, use %e. If you want a shorter or cleaner representation, use %g. Question: how do you convert a string to a floating point number in Go? Answer: in Go, you can convert a string to a floating point number using strconv.parsefloat. You pass the string and the bit size, like 64 for float 64 or 32 for float 32. Even when you use bit size 32, the function still returns a float 64, so you can safely cast it to float 32 if needed. Parsefloat can also read special values like +infinity, NaN, and scientific notation such as 1.5 E10. Question: how do you convert a float number to a string in Go? In Go, you can convert a float number to a string using strconv.formatFloat. You give it the number, a format like F or E, the precision, and the bit size. For example, using format F with precision 2,
turns 3.14159 into the string 3.14. If you use precision -1, Go chooses the smallest string that still represents the value correctly, like turning 0.1 into the string 0.1. Question: what are some important functions in the Go math package? Answer: the Go math package provides many useful functions for working with numbers. Math.abs gives the absolute value. Math.sqrt finds the square root. Math.pow calculates a number raised to a power. Math.log, Math.log2, and Math.log10 find different types of logarithms. Math.exp gives e raised to a number. There are also functions for trigonometry, like Math.sine, Math.cos, and Math.tan, which use radians. Math.Mod gives the floating point remainder, while math.Remainder gives the IEEE 754 remainder, which is slightly different from mod. Question: what is the difference between math.Mod and math.Remainder in Go? Answer: in Go, math.Mod and math.Remainder both calculate a remainder for floating point numbers, but they follow different rules. Math.Mod returns a result that has the same sign as the first number, and is usually what people expect from a normal modulo operation. Math.Remainder follows the IEEE 754 standard, and its result can be negative even when both numbers are positive. Because of this, the two functions can return very different results for the same input.
Question: when should you use math.Big.Float in Go? You should use math.Big.Float in Go when you need very high precision for decimal numbers. Unlike float64, big.Float can use any precision you choose, such as 256 bits, and it grows as needed. This is useful for things like financial calculations or scientific work where rounding errors are not acceptable. You can do math operations like division, parse long numbers from strings, and compare values accurately using methods like quo and CMP. Question: why do nan and infinity cause problems when encoding floats to JSON in Go, and how can you fix it? In Go, JSON does not support special float values like nan or infinity. If you try to encode a struct with a float64 value that is nan or inf, JSON.Marshall will return an error. A common fix is to create a custom float type with a Marshall JSON method. In this method, you check if the value is nan or positive or negative infinity, and convert it to a string like nan, plus inf, or minus inf. For normal numbers, you encode them as usual. This way, your JSON encoding will not fail. Question: why are sorting and comparing floating point numbers tricky in Go? Sorting and comparing floating point numbers in Go can be tricky because of special values like nan and the difference between +0 and -0. If a slice contains nan, sort.float64s may produce an unpredictable order. In newer Go versions, slices.sort handles this better by placing nan values at the beginning. For strict and correct comparison of all float values, including nan and -0, you may need a custom comparison that works on the raw bit representation of float64 values. Question: why is it dangerous to use float values as keys in a Go map? It is dangerous because float numbers are not always equal when they look the same. For example, 0.1 plus 0.2 is not exactly equal to 0.3, so the map treats them as two different keys and stores two entries. NaN is even worse because you can add it as a key, but you can never find it again, since NaN is never equal to itself. Also, +0 and -0 are treated as the same key, so one can overwrite the other. Because of these problems, float should not be used as map keys in production code. Question: what are subnormal numbers in Go float64, and why do they matter? Subnormal numbers are very small float64 values that are smaller than the smallest normal float64 number. They allow numbers to slowly go towards 0 instead of jumping to 0 suddenly. This is called gradual underflow. The problem is that subnormal numbers lose precision as they get smaller, so calculations with them can become less accurate and sometimes slower. Question: Why should you not use float numbers for money calculations in Go? You should not use float numbers for money because they cannot represent decimal values exactly. This can cause small errors. These errors are bad for prices and totals. A better way is to use integers, such as storing money in cents, or use precise types like math big rat.
Question: why does adding 0.1 many times in a loop not give the exact result in Go? This happens because 0.1 cannot be represented exactly as a float number. Each time you add it, a very small error is added too. After many repetitions, these tiny errors build up. This is called accumulation error. As a result, the final sum is slightly less than 100, and comparing it directly to 100 gives false. Question: how does the Kahan summation algorithm fix float accumulation errors in Go? The Kahan summation algorithm reduces small rounding errors that happen when adding many float numbers. It keeps an extra variable called compensation that tracks the tiny lost bits from each addition. Then it adds them back in future steps. This helps make the final sum much more accurate than normal addition, especially in long loops. Question: what is a common mistake when doing division in Go that is meant to produce a float result? A common mistake is dividing two integers and expecting a float result. In Go, if both numbers are integers, the result is integer division, so 7 divided by 2 becomes 3, not 3.5. To get a float result, at least one value must be a float, or both integers must be converted to float 64 before dividing. Question: what happens when a float value overflows in Go? When a float value becomes too large in Go, it does not cause a panic or error. Instead, it silently turns into positive infinity or negative infinity. For example, multiplying the largest float 64 by 2 results in inf. This can be dangerous because the program keeps running, but the number is no longer a real value. You must check for this using functions like math.Inf. Question: why does converting float 32 to float 64 not make the number more accurate in Go? Converting a float 32 to float 64 does not add precision because the original value was already rounded when it was stored as float 32. When you convert it to float 64, Go only keeps the same rounded value but shows it with more digits. The extra digits are not real accuracy. They just reveal the old rounding error. Question: when should you use float 32 instead of float 64 in Go for performance? You should use float 32 when memory use and cache performance are important, such as in large arrays, graphics, or GPU-related work. Float 32 uses half the memory of float 64 and allows more values to fit in CPU vector registers. However, Go uses float 64 by default, and the standard math package works only with float 64. Using float 32 often requires extra conversions or third-party libraries, so float 64 is usually the better and simpler choice unless performance or memory really matters. Question: what is the difference between complex 64 and complex 128 types in Go? In Go, a complex 64 number is made from two float 32 values, one for the real part and one for the imaginary part. A complex 128 number is made from two float 64 values. If you write a complex number like complex 3.0, 4.0, Go makes it a complex 128 by default, so both parts are float 64. You can use real and imag functions to get the real and imaginary parts separately. Question: what does unsafe bit manipulation with floats do in Go, and why is it risky? Unsafe bit manipulation lets you look at the raw binary bits of a float value without converting it. For example, you can treat a float 64 as a UN64 and see its exact bit pattern in memory. This is useful for low-level work, like debugging or implementing special numeric logic. However, it is risky because it bypasses Go's safety rules and depends on memory layout. A small mistake can cause bugs or crashes. In most cases, it is safer to use functions like math.Float 64 bits instead of unsafe.
Question: how can you use float 64 values safely with atomic operations in Go? Go does not provide atomic operations directly for float 64 values. To work around this, you can convert the float 64 to its raw bits using math.Float 64 bits and store those bits as a UN64 with atomic operations. When loading, You convert the bits back to float64 using math.Float64 from bits. This makes the read and write atomic. Even in Go 1.19 and later, there is still no atomic float64 type, so this wrapper pattern with UN64 is the correct and safe approach. Question: why should you not use double equals to compare float values in Go tests? You should not use double equals to compare float values because floats often have tiny rounding errors. Two numbers that should be the same may differ by a very small amount. Instead, tests should check that the difference between the values is within a small tolerance. This makes tests stable and correct. Libraries like Testify provide helper functions that do this comparison for you. Question: why should you avoid using float types for decimal or numeric columns when working with databases in Go? Decimal and numeric database types are meant to store exact values, like money. If you scan them into float32 or float64 in Go, you can lose precision because floats cannot represent decimal values exactly. This can cause wrong prices or totals. A safer choice is to scan these values as strings or use precise types like big rat. Float types are only suitable for real or double precision columns. Pros-Cons summary. Quick decision guide.